Hi, welcome back to physics. We've been studying waves, and in particular, light waves most recently. We just learned about the law of reflection, which tells us that the incident angle of a ray of light which encounters a barrier will exactly equal the reflected angle, as measured from the normal to the surface. This law describes how mirrors work, as well as one of the interactions when light waves encounters some obstacle. Today, let's take a look at something called c, light speed. Light speed gets its own cool name because there is only one speed for light. As long as there's nothing in the way, every kind of light in the universe moves at the same speed, just under 300 million meters per second. Whew, that's pretty fast. The caveat comes that light actually doesn't always move that speed, because sometimes there is something in the way. Air isn't much of an obstacle, so light speed in the air is almost exactly the same as c in a vacuum. Other material objects, though, like, say, water or glass, have a much larger effect on light and slow it down significantly more. That changes a lot about their optics and the behavior of light, as we'll see soon. But let's take a look at some examples of what light speed means. Since light has such a nice, constant, consistent speed, and because it's the fastest thing in the universe, that allows you to translate distances into times. For example, your phone being about a foot away from your eye means the image that you're seeing on it was released from the phone about 1 nanosecond before you actually see it. It takes that much time for the light waves to propagate through the space between your phone and your eye. The moon is a little further away. It takes about 1.2 seconds for moonlight to reach us from the moon. The sun, further still, takes about 8 minutes of time for that light to traverse that space between. A little farther out, the closest star to Earth is called Proxima Centauri. It's about 4.3 light years away, meaning the light that shines from that star takes 4.3 years of moving at c before it can reach us and be seen. And finally, there's a gigantic supermassive black hole in the center of the Milky Way galaxy called Sagittarius A. And it's about 25,000 light years away, meaning it doesn't emit light, but if it did, it would take that light 25,000 years to get to us from the center of our galaxy. Again, since this is such a well-known and universal constant, c is a useful thing in physics. Let's try a couple examples and see what we can learn about light. So first of all, page through your reference table and see if you can find what frequency represents yellow light. Try to find another one for green light. Now, if I shine light at you with frequency 4.9 times 10 to the 14 hertz, what would that look like? What color would it be? What if I changed it so it's now 5.15 times 10 to the 14 hertz? What color would that be? Finally, if I shine a violet light of 6.70 times 10 to the 14th hertz frequency, do you know what its speed would be in a vacuum? And what its wavelength would be? You should be able to do all these. Pause it for a moment and see if you can. Okay, so hopefully you gave this a try. Let's take a look. First of all, yellow light. So each color of light is represented by a range in the spectrum, which is found on the top of page 2 of that reference table. So yellow light is found between 5.03 and 5.2 times 10 to the 14 hertz. So anything in that range would represent to your eyes as yellow. So we could say 5.1 times 10 to the 14 hertz for that first question. Green is a slightly higher frequency. It's the next one up. So it's anything between 5.2 times 10 to the 14 and 6.1 times 10 to the 14 hertz. So you could say 6 times 10 to the 14 hertz would represent a green ray of light. The next question, if we look at a light of 4.9 times 10 to the 14 hertz, that would be an orange light. The next one of 5.15 times 10 to the 14 hertz would look yellow to your eyes. It falls within that yellow range. Finally, for violet light, we should know what its speed is in the vacuum because all light moves the same speed, c, which is 3 times 10 to the 8 meters per second. And we can use the wave speed equation to figure out its wavelength knowing its frequency. V equals frequency lambda could be solved to get a wavelength of 4.48 times 10 to the minus 7 meters, which is 448 nanometers. For historical reasons, we've typically measured light wavelengths in terms of hundreds of nanometers, and you'll see that going forward. So what does it mean that light's going to be moving slower? Well, it turns out that when light rays encounter a change in medium and their speed changes, the outcome from that is a change in direction. We call this refraction. Toss a pencil into a glass of water, and you'll see what I mean. It looks like it's broken in the middle because the light coming off the pencil through the air looks normal, but the light coming off the pencil moving first through the water, then through the air, has to bend and change direction partway through, so it distorts it and makes it look different. This happens because the speed of light actually changes at that interface between water and air. So in a qualitative sense, what we're looking at is this change in direction based on the speed change. If you're moving from some fast medium, like air, into a slower medium, like water, well, the angle is going to shrink. Your ray is going to bend towards that normal line that we drew last time. And again, the normal is the perpendicular to the surface line that we sketch in at the point where the ray hits the surface. So you can see in our first example, theta 1 is larger than theta 2. That angle is bigger in the faster material than the slower. So as it's moving towards the bottom of the screen, you'll see it bend towards that normal line. The second example on the right shows light moving from a slower medium towards a faster one, for example, from water out into air. And in that case, you'll see that light ray bending away from the normal. In other words, the second angle, theta 4, is bigger than the first one, theta 3. That happens because as the light ray leaves the first material and moves into the second one, it actually speeds up, which makes it turn. This effect, it's larger the bigger the angle is. So if your theta incoming is 0, i.e. if you're coming straight down the normal and the light ray hits perpendicular to the surface, there's no refraction at all. But the larger the incoming angle is, the more you'll see this refraction effect. You might have noticed this if you look face on to a big aquarium. If you look straight ahead at a fish, it looks normal, but looking far to the left and to the right, frankly makes me feel nauseous because everything looks so funny. The refraction effect is so strong as that angle gets bigger. So that's an introduction to refraction in a qualitative sense. Thanks for learning with me today. I'll catch you next time for more physics.